Skov. And okay, I gotta click this here. Okay, we are recording. Tonight, we have a very special guest, Dr. Tamitha Skov, WX6WW. She is known as the Space Weather Woman. She's a new kind of weather forecaster for our modern world. She will introduce us into this weather forecasting concept and will educate us on various aspects of how this all ties into our world of amateur radio. We will have questions and answers at the end. If you would, please all mute, have your questions ready. All you'll have to do is put your hands up, we'll call on you, and all you have to do is unmute and unmask and ask your questions. So keep your questions at hand. Thank you so much for being here. So go ahead, Tamitha, the Zoom is yours.
Wonderful. Okay. Hello, all. Hopefully, at least some of you know who I am. And if, just in case you didn't see, I think Keith just left a message in the chat. If I'm someone who doesn't share, like do a screen share, I have because of my green screen, I use my slides in the background so I can point, because I'm very, animated that way. And I think it helps. So if you are looking at me in a gallery view and I'm just this tiny little thing and you can't see what's going on, you can pin me by clicking, I think, the top 3 buttons. If you're on a laptop or even on a tablet, you push a button where you see those 3 little buttons and it'll say pin, I think pin to top or something like that. And then it'll make me big and then it won't change. So then you can follow along, because the slide should be completely readable. And then afterwards, if anyone wants, let's say, a PDF copy or something to catch up if something wasn't quite clear, or you just want to keep them for posterity, just, I guess, let Brad know or someone else know, and they'll ping me to send some copies along. So anyway, thank you for joining me. This is basically a talk that's going to be like an overview of space weather to some degree, but I am going to throw in it, since we're all amateur radio operators, I am going to throw in there a little bit about what the new cycle means when it comes to radio propagation, and maybe give you a little bit more insight into how the ionosphere kind of, the upper atmosphere, how it kind of works with space weather and terrestrial weather, and all the fact that it's just kind of like, you'll see at the end, that it's pretty much like a big Oreo cookie. It's kind of the cream of the Oreo cookie. It's kind of sandwiched between both, from the above and from below. And that kind of sandwich really makes it a very complicated region to understand, which is why amateur radio and trying to predict how well radio propagation is going to fare at any one time can be extremely difficult. So first, I'll start off with those of you who know anything about my history. I am a space physics person. I was a space weather physicist. I was never meant to be an amateur radio operator, at least I didn't think at first. And I started getting on social media for something completely different, for music. And when I started talking about space weather online, suddenly a bunch of amateur radio operators just started coming out of the ether, so to speak, and asking me really intelligent questions. And I learned very, very quickly that a lot of radio amateurs are very tech savvy. You all are engineers, or you have some understanding of non-trivial things. And the funny thing is, as I continued to answer questions about space weather, I realized that you all belong to a very key group. Of course, you belong to this group here, right? You're the emergency radio responders, first responders in lots of types of emergencies. You work the ARRL. There's a ton of you all over the place, and you guys are on the front lines of space weather, because with HF radio, anything that space weather can dish out, HF sees. So all of you have dealt with space weather really, I don't want to say on a day-to-day basis, but yes, a lot of times you actually are. Now, interestingly enough, though, you're not the whole reason why space weather even exists. I mean, really, it all started with these groups down here, right? The Power Grid Company, the Homeland Security, all the government agencies, the FAA, right? All of this is really where it all started. And then as as national security space became a thing, as the civil and commercial industries became a thing. Right now we're doing SpaceX and O3B and Amazon. All these groups are now really launching the civil and commercial area of space. Of course, Virgin Galactic, and now we have Hotel ISS and all the people that want to do aurora photography, whether it's on the ground or in space. That's another group of people who are very interested in space weather. And of course, the emerging GPS industry, right? Now, for the military, GPS has been around forever, it seems. But when it comes to all the neat gadgets that civilians get now, GPS is exploding. I mean, even the emerging drone industry, which is now beginning to get so big that they're partnering as like real transportation networks for civil aviation authorities. So it's unbelievable how we actually have, like in Canada, the Canadian Transit Authority is actually partnering with big drone companies, because a lot of places up there don't have viable roads, or the roads get washed out during big storms. And so they have no way to transport, things like medicines and food and even organs, believe it or not, to some of these really distant, really, remote locales. So they're using drones. But the funny thing is, space weather affects all of this stuff. So it becomes an issue even for space enthusiasts. So those people down here who just really like space because they like space, those people, those are the ones I expected to see. But instead, I got all of this on social media, and that really began kind of this real dive, a real kind of paradigm shift in my mind in terms of, wow, I mean, there's really a lot of need out there for space weather that I had never knew existed. So to kind of start off with what really is, I'll stand over the words for the moment, since the pictures are probably more fun to look at. So before I dive into some of the details of space weather, let's just talk about what space weather really is, and really how a scientist looks at it. Because, space weather, if you notice, terrestrial meteorologists, your typical weather person on the news, is not talking space weather. They're talking about the storms, they're talking about the sun, they're talking about the cold fronts and all that stuff. But you never really hear them talk about space weather. And if you're one of the, I'll say, unlucky ones who have, they most likely told it wrong. They most likely did not, they mixed up the words. They had no idea what they were talking about, because they're not trained in it. Because to most people, space weather is an academic field. It's more closely related to astronomy than it is to terrestrial weather. So to a scientist, a space weather is considered a planet's interaction with its host star, okay, and then the surrounding space environment. And that sounds pretty spacey, right? And when a scientist looks at space weather, they look at the space weather around, moons and planets and comets and asteroids, anything that floats around in space, we're looking for space weather around. And so there are so many other systems that are much more exciting than Earth to look at space weather. For instance, you see here's the Saturnian environment, right? You can see the aurora around Saturn. You see Saturn's rings, of course, but there's aurora at the poles. Over here is Jupiter, this one over here. Whoops, you can see the purple, get my hand in the right place. Here's the purple aurora at the North Pole in Jupiter. Here's another look at Jupiter's aurora. And in fact, the Jovian environment is such a neat environment to space physicists, because if you notice here, if I move my hand to the outside, do you see this weird little, kind of like, looks like a comma? This, believe it or not, is the foot point of Io, one of its moons. Believe it or not, they're magnetically connected, both Jupiter and its moon. And so aurora kind of jumps, the things that cause aurora, the particles that cause aurora, actually jump back and forth between Io and Jupiter. And then, believe it or not, if you can see a couple other dots, there's Callisto and Ganymede, two other moons. So all of that is like this big coupled system in Jupiter. And so, of course, scientists are much more interested in looking at that cool environment than looking at Earth with its very boring atmosphere-less moon. And, it's just kind of dull. So that's the sad thing about space weather, is that Earth really doesn't get that much attention, when in actuality, it needs to get as much attention as typical meteorology. Now, as I've already said, we see aurora, and we see aurora at planets. We also see them at moons. We see it even at comets. I mean, we're actually now looking at, just even with Parker Solar Probe, we're looking at aurora at Venus. We're looking at aurora at Mars. We just saw one with an asteroid not that long ago. It's pretty amazing what we've been able to detect as scientists. But outside of the sun, there are other effects. There are other types of space weather. We have things like cosmic rays. We have things like micrometeoroids and interstellar dust, and of course, space junk, the man-made stuff. And a lot of times those get a lot more attention as well than does just plain old space weather at Earth. So it's really no wonder to a scientist why there isn't all that much work being done at Earth. Because, you know, academically, it's not all that interesting. Meanwhile, this is what you guys get to deal with, right? It doesn't really affect all that much, just little things like satellites and communications and airline transportation and national utilities and power grids, right? Geolocation services, satellite radio and television, satellite wireless and mobile technologies, the Internet of Things, unmanned aerial vehicles, right? On the drone industry, we already talked about it. And of course, the emergency disaster rescue and release services. We can do without that. You can see why that's not so important, right? It's just little things. Wrong. And this is what really launched me. This is why I became overwhelmed very, very quickly when I got into, got on online and started answering questions about space weather, because it became very clear very quickly that there was this massive need that was going completely unfulfilled. So that started my journey, and it's been a very unique journey. And I am going to take you through a little bit of that journey. Not too much, but I'm going to focus mainly on the things that are, that I can squeeze in less than an hour, that are very relevant to you all. So the first thing I'm going to do, because this is the type of thing I get a lot of questions about, is really what's our star about? And when I see a purple sun or a green sun or a yellow sun, what in the world is all that? So let me tell you about the main eye candy that we get with space weather, and that is the Space Telescope SDO, and that's what these images are down here, and I'll talk about them in just a second. But before I do that, I want to first let you know that our star, unlike just being a plain light bulb in the sky, it is actually more like a lava lamp, okay? It's always changing, and it goes from being very quiescent, very quiet, like when a lava lamp is turned off, to after a lava lamp's been on for an hour or two, it's kind of bubbling and gurgling and constantly moving. And that would be the sun when it's active, right? And in actuality, we're beginning to start that process now. Just recently, someone turned the light on the lava lamp again, and so now the sun is starting to act up. I don't know if you've noticed in the news, but stories about the sun and what it's been doing lately are beginning to pick up again. Well, this is the solar cycle, and we will talk about it. And really, it's all part of the process of this giant fusion reactor that is driving space weather. And you can imagine it's driving space weather on a cycle, right? And the sad thing, though, is that space weather isn't simple. And there's lots of different ways that this giant fusion reactor, this big RF generator, can actually create space weather. And its output, its energy output, comes out in all sorts of different forms. And I'll stand on this side now so you can actually see the words. So we get stuff like electromagnetic radiation from X-rays all the way down to radio waves, and obviously radio waves should perk your interest, right? We also get things like solar wind, right? This is both plasma. Now, a plasma is simply a gas that's charged. That's all it is. So really what happens is that when you put a lot of energy or electricity and magnetic fields into a gas, the particles separate. The ions and the electrons, instead of being neutral particles moving around like you have in a normal gas, those separate. So now you got pluses and minuses running around. And those pluses and minuses, they see electric and magnetic fields, so they must obey them. They have to obey them just like they obey, the law of gravity. And that's the difference between a neutral gas and a plasma. A plasma sees electric and magnetic fields and is moving around according to it, feels them as forces. So we get a lot of plasma and magnetic field from the solar wind. We also have things like solar flares, and that's where we get radio blackouts, which I'm sure you've all have experienced those. I call that when the sun is screaming. And then we also get solar energetic particles. Those are radiation storms. And then of course we get coronal mass ejections, which we also call solar storms. But you can imagine with this much stuff going on the sun in terms of space weather, how complicated is that? And because of that, we actually as scientists, have to look at the sun in many different ways. And really what it is, and this is where we start getting all the different colors when it comes to the sun when we look at it and when we're looking for particular things. If you think of the sun as from the surface of the sun out through its atmosphere, right, which we call the corona, if you look at it as like an onion, And, all the youngins have layers. And if you peel the layers, you can kind of go further and further down, or in this case, further and further up from the surface of the sun to be able to see what's going on in each layer, right? How we do that with the solar telescope in space is that we do it with temperature, right? So each temperature really dictates a different layer in the atmosphere. And so as scientists, we color code them. So for example, this down here, this is actually the only color you can actually see down on the ground. This is the surface of the sun, and we see it in white light. Believe it or not, our atmosphere actually blocks out all this other stuff. It absorbs all this other energy. This is why you only see these crazy looking views of the sun from space. It's not CGI, I promise. It's what we call extreme ultraviolet. Our atmosphere shields us from that. It's not part of that atmospheric window. So sadly, from the ground, this is all you're going to see. Something similar to this, or maybe a calcium line, okay? Now, if we go up, when that's 5,700 degrees Celsius, okay, that's the temperature of that light. Now, as we go up a little bit higher, this is, I think, 1,700 angstroms. This is where we begin to see a little bit more of the details around the sunspots. We call them plages. So you're beginning to see this, believe it or not, this same sunspot that you see here, it's actually being shown in this image too. And you're seeing a little bit of the white stuff around it. Believe it or not, that white stuff actually creates some of the bright points, and it actually causes some of that F10.7, the solar flux that you're so used to. It's actually the bright points that give us a lot of that. Now, if we go a little bit higher in energy, we get to 304 angstroms, and now we're beginning to get at a higher layer. We're getting into the transition region between the surface and the solar atmosphere. And there's so much dynamic stuff going on. As a matter of fact, this is where you see those massive eruptions where the sun is literally belching stuff off and just shooting it out into space. This is a loop from what we call a coronal mass ejection. So that's a solar storm launching right now. And then as we move up even higher in energy, we can start seeing even more of that tenuous atmosphere. You see it kind of streaming out in this purple sun. This is 211 angstroms. And we see coronal holes. See this black or this dark thing right here? This is the origin of fast wind. When we get fast solar wind, this is where it comes from, things like coronal holes. You don't see it in 304, but you do see it in the higher wavelength. We go up even higher in energy, and we can start seeing loops with magnetic fields, all sorts of differences, when blast waves, when big eruptions occur. So it allows us to see even further up in certain details we wouldn't see in another layer. And then if we go up into some of the highest energies in EUV, this is 131 angstroms. This one allows us to see solar flares really, really strongly. And I'll show you a detailed image of that. And believe it or not, all of these images, it may not look like it, but every single one of these images was taken nearly at the same time. So see how incredibly different the sun can look. As a matter of fact, if you look really closely in this image, whoops, in this 131, you can see that little coronal loop? See that loop coming out? It's the same thing that you see in 304 in red, right? So these were all taken really, really close to the same time, but they tell us a different story. And so when a scientist looks at these images, and they say, well, what's the blue sun? You immediately go 131 angstroms. What's the gold sun? 171. We just know it. Boom, 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 boom. So it helps us to color code them this way. Sadly, and some of you might actually wonder, well, if it's a different spacecraft, are the color codes the same? No, there's no convention. So you just kind of have to memorize. Scientists are good, but they're not that good. Every mission has its own color code. So sadly, if you ever look at stereo data, you'll see the stereo data is color coded slightly differently, and a green sun on stereo is not the same as a green sun here. So sadly, we do that. But luckily for you, you don't really have to worry about all of that stuff. I mean, some scientists will say, okay, if you want to learn space weather, and they just give you all this jargon and all this crazy stuff, and there's all this complication, and no. Let's just boil it down to the things that matter to you, okay? And we really can just boil it down to 4 basic types of phenomena that affect Earth. 2 of them I guarantee you know quite well, but sadly, these 2 get confused all the time. Solar flares and coronal mass ejection, or coronal mass ejections and solar flares, which side is which. Let's talk about solar flares first, okay? This is a solar flare. Now, the sad thing is that solar flares and coronal mass ejections are launched most of the time near simultaneously. And so they oftentimes get confused, and that's why people say that they're the same thing, but they're 2 totally different phenomena. let me play the movie of the solar flare, and you should see it. Boom, right there. Okay, that solar flare, that is simply electromagnetic light. Okay, so this is X-rays all the way down to radio waves, travels at the speed of light. So as soon as we see it at Earth, it's when it's happening. I mean, it takes 8 minutes to get from the sun to Earth. As soon as we see it in our telescopes, you're feeling or hearing the sound pick up on the bands. You're getting that static. You're getting that radio burst. You're getting that drowned out, nasty radio blackout. Okay, that's what that is. That's caused from the solar flare. Now, this only lasts maybe a couple hours if it's a big one. It'll last a couple hours, and if you can't see the sun, you don't hear this. You don't hear the sun scream. So you don't get the radio blackout if you're on the night side. Only the people on the day side get it, okay? However, it's not the same thing as a solar storm. Oftentimes, a solar storm will be launched during a solar flare, but this thing is much bigger and much slower, and it does something totally different. Remember that loop I showed you? Watch it come out. So on this side, you're seeing the sun, real close image, and you're seeing that loop. Now I froze the image so you get a nice look at that loop, because we move out to this side of the image. The sun is this tiny little thing in the middle, and as the movie continues, you'll see this thing move further and further out. Okay, so now we're looking at a coronagraph view, and in the coronagraph view, this actually goes out to like 15 sun lengths out. Okay, do you see that loop? And I'm going to pause the movie right here so it doesn't get too far out. If you look on the side where the sun is, hopefully you can still see it. You can see this, the edge of this thing, the legs of this thing still attached to the sun. But this thing, if that's the sun here, right? And now we're looking out at coronagraphs. Hopefully you guys can see this faint loop that comes out. I'm not doing a great job outlining it, but here it is. It keeps that same shape, even as it comes out. Remember I was talking about plasma, how it's charged, and so it sees the electric and magnetic fields? Well, what's threading this loop are big magnetic fields, and it jails that plasma. So we're able to see it even out this as far away from the sun as this, simply because it keeps that same shape, simply because the magnetic field is still acting as that jail. Now it's getting bigger and bigger and bigger and expanding, but it's keeping that same shape simply because of those magnetic fields, and it has to obey. It's frozen into it, which helps us scientists, thank goodness, because we're desperately trying to predict these things. When these things hit Earth, they are the ones that cause aurora. Okay. Now this structure, as you can imagine, is much more massive than a solar flare. There's nothing going on here but light. But with this structure, it travels a lot more slowly, not traveling at the speed of light. It can get to Earth in about, anywhere between, the really fast ones can get to Earth in less than a day. Oh my goodness, those are the scary ones. But we don't have those very often. Most of them get to Earth between 2 and 5 days, okay? And they cause the big Earth reaction. They are the ones that hit our Earth's magnetic shield. They cause it to warble and buckle and change. And as they do that, the Earth's shield releases energy by pumping stuff down into the upper atmosphere, both in the north and the south, and it causes the aurora. And that's how we kind of dissipate all that energy from these structures, okay? So these cause big, what we call geomagnetic storms, and they can last for days. And they affect you mainly on the night side, okay? Solar flare, day side, and fast. Like as soon as you see it, you get a radio blackout on the day side. These structures, which people confuse as being solar flares, these don't arrive in 8 minutes. They arrive in 3 days, okay, ish, give or take an ish. And they cause problems for you on the night side, mainly. Okay, so totally different phenomena, and yet they're often confused because they both oftentimes launch together. Okay, they don't have to. You can have one of these without one of these, and you can have one of these without one of these. But most people don't know that, and definitely the meteorologists that try to do space weather that aren't trained properly only get everybody else confused because they keep using these names interchangeably. So that's part of the problem. If you've ever tried to understand space weather and had a hard time, that's most likely why. Now, here's another one, radiation storms, and I'll play this movie. Radiation storms are those super energetic particles, and I'm playing the coronagraph. Remember the image from here? So this blue part of this image here, This is the coronagraph. So you're seeing the outer atmosphere of the sun, and you're seeing a lot of coronal mass ejections, a lot of these solar storms being launched out. But not just that, there are also what we call energetic particles, these radiation storms that get launched every now and again. And you'll see one here pretty shortly. You saw a little one there. It's a little bit of a blizzard, but you'll see why we call it a blizzard in just a second. Boom. See that? Massive. Boom. There's another one. Let's see if I can pause it when another one comes here. Come on, there's a few more. This was the Halloween storms, if anyone's interested. Oh, come on. If anyone's interested in that time period. This was during the Halloween storms that were just incredibly intense. Strangely enough, when radiation storms happen, this is what astronauts see. They can actually close their eyes and they see these pinpricks. They actually get fireworks in their eyes, because what's happening is that super energetic particles are bombarding or slamming into, in this case, the detector. This is a camera detector. It's the same like the CC detector that you have, or CCD detector you have on your, in your cameras. And these energetic particles slam into that detector and deposit energy. And when they do that, it tricks the detector into thinking that there was light hitting it. So you get these streaks, and they come in all different directions. But strangely enough, your eyes do the same thing. So when astronauts are in the ISS, for example, and there's a big radiation storm, they have to hunker down, and they can actually see these more often, much more particles hitting their eyes and having these fireworks going off. So they know they're in the middle of a radiation storm. We can't shield them. But we also get, because of that, when those particles end up hitting the upper atmosphere, you actually get, here's a map of the world. This is actually a model called DRAP. Some of you might actually know it. But you get these big radiation storms up at the North Pole region and in the South Pole, just kind of like aurora, because that's where our Earth's magnetic shield is pretty much open to these particles. They can just kind of stream on in. And so they cause problems for us both at low and at high latitudes, both in the south and in the north. So that's one other thing. And radiation storms are driven by both solar flares and coronal mass ejections. So there's 3 phenomena. Now the last one is simplest. This is a coronal hole. You can see this big black, what looks like a tear across the sun. No, it's not really a hole. As we saw from the previous slide, if I looked at this sun in a different color, you wouldn't see a hole. All it means is that the sun is not emitting light in this wavelength, and so it looks like a hole. It just means it's cold in that sense. And we know from these images, from the images and from sampling these regions, what we get from these regions is fast solar wind. So it's like a boat plowing through a slow stream. You get that bow wave coming at you. And that same kind of thing happens in the solar wind if you think of the wind as like a river. Once you get that fast stream coming at you, it slams into the slow stream ahead of it and kind of creates this wave of stuff that wants to now slam into Earth. And it mimics one of these. So you end up getting something very like a solar storm from fast solar wind. Okay, and you always know, because you can always see these coronal holes as they come across the Earth, the face of the sun. We'll end up getting into a fast wind stream, and it'll cause a storm, like what we've just had over the past couple of days. Believe it or not, we had a small storm, and it was due to a small coronal hole. So hopefully that's reasonably clear as mud, right? But that's about it. I mean, there's just 4 basic phenomena that you worry about, and even with coronal holes and the fast wind, it acts very much like a coronal mass ejection, which basically just creates solar storms. So if you can keep the idea of solar storm, solar flare, and solar radiation storm separate, you pretty much got it in a nutshell. It's not too difficult. The other thing that makes things more complicated, or seem more complicated than they should be, is the fact that we have a solar cycle. There are times when certain things are, certain types of phenomena happen more often than others. And in this case, we're talking about solar maximum, solar minimum. I'm sure you guys, these are names that you've probably heard. If you've been a radio amateur for a long time, some people even count their lives in terms of how many solar cycles they've lived through. So, it's kind of a neat way of looking at it. But a solar cycle is essentially about 11 years. And here is a long, some of you might have actually seen a plot like this before, where you actually have time moving across the bottom. And this is over a very long period of time, from 1600 up to about the present day. And you're seeing sunspot number on the vertical axis. So way back when, in the 1650s or so, there was about 75 years of basically no sunspots. Now, we didn't know that through direct observation. In actuality, what all this red data here is actually from ice cores. We did proxy, so this is a proxy measurement. It wasn't a direct measurement. We started getting direct measurements, meaning, you know, amateur telescopes on the sun right around 1750, and that's actually when we started counting solar cycles. So as you can see, you go up, down in blue, up, down, up, down, up, down, up, down, about every 11 years. That's the solar cycle going up and down. The sunspot number at solar maximum is high. The sunspot number at solar minimum is 0, kind of thing, up, down, up, down. But if you notice, the average, which is this black line, that kind of smoothed average through there, shows you that it's really the sunspot cycle is not constant. It's not like a light switch that turns on and off and on and off, and every cycle it's exactly the same over and over again. It's really not. There's a lot of other pseudocycles that go on that modulate how active our star is over time. And so we get about 5 to 7 years of activity, and then we get quiet for about 5 to 7 years. Depends upon how active the cycle is to how long the cycle lasts. The more active the cycle, the shorter it is. The more quiet the cycle, the longer it is. So, you know, there's a little competition going on between really competing cycles internal to our own star. It's not just the 11-year cycle acting on its own. There's other things going on that are tugging that cycle, making it longer or shorter and higher, you know, more sunspots or less sunspots, depending upon what is really happening. And I'll talk a little bit more about that in just a second. But that causes issues, of course, for scientists, because wouldn't you know it, right as we get into the space age and we really just get comfortable with our star, our sun decides to do something squirrely. It decides back in 2000, really about 2004, to take a breather. And it decides to go into this really deep minimum and take a long time to come back to life. And at that time, everybody started screaming, oh my gosh, grand solar minimum, the sunspots are going away, we're going into another maunder. And some scientists got really, really happy and decided to say, yes, this is exactly what's going to happen. And, you know, we're not going to have another solar cycle until the year 2060 or something. And oh my goodness, yes, they were wrong. But what they were not wrong about was the fact that we did have a huge transition at that time. Basically the cycles since about solar cycle 22, which was, I think, in the 80s, early 80s, maybe late 70s. We'll see a plot about it in just a second, so that will re-jog my memory. But since about solar cycle 22, things have been kind of calming down a little bit. And that has been like freaking people out to you know, to put it mildly. Scientists have been really trying to figure this out since about 2004, when they really started seeing things change. And yes, we've finally been able to come to a consensus to some degree, but there's still a lot of there's a lot of hot debate regarding that. What we have been able to come to a consensus about is that we are not dipping into another Maunder minimum. We are having slower cycles, and that means we have lower luminosity, we have lower activity peaks, there's less sunspots, and the cycles have been consistently going downward. So yes, we're in a grand solar minimum from that perspective, but it's not going to be deep like the Maunder. Okay. Now, what this also means, of course, is that when our cycle gets weaker, our sun gets weaker, our sun has this big magnetic shield around it, and it shields out stuff from the outside. In fact, it shields our entire solar system from all the junk that's beyond it, that's in interstellar space. And what we worry about are cosmic rays, because those cosmic rays from big supernova explosions and all sorts of other things that are going on in interstellar space, that stuff seeps into our solar system and down into the Earth's upper atmosphere. And that can cause problems for astronauts, can cause problems for airlines, can cause problems for avionics, can cause, I mean, there's all sorts of things that can cause problems for satellites. And what we've noticed was with these weaker cycles, the cosmic ray flux is getting higher. And so that's become a much bigger deal to us in the last couple cycles. So sadly, space weather, even though people say, well, the sun goes to sleep, there's no space weather while the sun is quiet, that's not necessarily true. It actually means that we've got more space weather, but it's not from our star, it's from all the other stars out there that are beyond our solar system. So strangely enough, there really is no such thing as quiet space weather. It's just a change of the origin, the source of it. Is it our star, or is it the stars out beyond? So right now we are dealing with higher cosmic ray flux. That's going to be an issue, but thank goodness I think we've gotten through the maximum of that. As our star begins to ramp up again and wake up, its shield gets stronger, and so that cosmic ray flux is going to start going down, thank goodness. We had a minimum in about 2019 to 2020, but the problem that we're finding, and this is beginning to be, I don't want to say a consensus yet, but people are beginning to really understand it, or understand it's an issue, is that part of that sloshing, part of that reason why our star has, you know, these modulations, is that the northern hemisphere and the southern hemisphere don't always like each other. They actually aren't always in phase. And as radio amateurs, you guys know, right? It's like having waves in phase, right? If you have things in phase, they're going to amplify each other. If you have them out of phase, they could actually cancel each other altogether. Well, the sun's hemispheres are exactly the same kind of thing. If they are in phase, you're going to get, imagine if you have a certain number of sunspots that are coming from the northern hemisphere and a certain number of sunspots that are coming from the southern hemisphere. If you overlap them and they decide to maximize at the same time, well, you're going to get, you know, something that's twice as high, but short in time. If this is the distribution, let's say the northern hemisphere, and this is the distribution of sunspots in the southern hemisphere, here's the peak and the minimums down here. Then if you overlay those two, you're going to get something that peaks very, really high. They superpose, but it's not going to last all that long in time. It's going to be pretty short. But if those two hemispheres want to peak at different times, well, you put them next to each other, and sure enough, it's not going to peak as high. It's only going to peak as high as one of them. It's not going to be like this. It's going to be like this. But you're going to stretch it out, that distribution, totally in time. And you may even get a double peak. A double peak? You mean like one hemisphere peaks in sunspots and then it goes down a little bit and then you get another peak? Well, doesn't that look familiar? Whoop. How about this one? Right? See the double peak? So what do you think? This is our latest sunspot cycle. Do you think maybe the hemispheres were out of phase? Yeah. And guess what? They still are. So the funny thing is that caused scientists to really freak out, because we didn't understand the sun this way when we made the last prediction for solar cycle 24. In fact, you want to see scientists scramble. Back in 2008, we made a prediction for sun cycle 24, which is the cycle we just finished. And we predicted it was going to have this many sunspots about this high, and it was going to the maximum was going to happen in 2012. Well, in July 2009, we realized, okay, that was bad. Let's redo it. So then we made another prediction, and we said sunspot number was going to be, I don't know, less than 100, and sunspot maximum was going to happen in 2013. Well, that really wasn't good either. And then April 2011, we made another prediction, and it was that sunspots were really going to be only about 60, and the maximum was going to happen in 2013 and a half. So you can see people were scrambling. This is the scientific consensus for the last cycle. Can you tell scientists were a little bit biting their nails at the time? In reality, the prediction was a little bit better, looking at it around, at least for sunspot number, with our prediction in 2009. We had about 60 to 70. I can't remember exactly what the average, what the real sunspot number was officially, but it was double peaked. And the sunspot maximum didn't happen until 2014. So we still don't really understand it completely. In fact, when Noaa decided to make their consensus prediction, I don't know if any of you ever saw this, but I kind of laughed. This was their first prediction of solar cycle 25. I think it's a little blurry. Doesn't it look like you could just take this cycle, it's like the 24, pull it, throw it over here and fuzz it out a little bit? I don't know. Does that look very scientific to you? Not really. So as you can see, scientists were really shaky about solar cycle 25 because we did so badly in solar cycle 24. And in fact, now we have solar cycle 25, labeled. We think it's going to be about 150. The consensus is that cycle will happen, the maximum will happen in 2025, and it'll be 115 sunspots, essentially what cycle 24 was. Notice, however, there's only one peak, right? That's because the consensus doesn't look at hemispheric asymmetry. They talk about hemispheric asymmetry as being the reason why this prediction, if it's wrong, that's why it's wrong. And they kind of feel like we dodged a bullet. We can just blame it on hemispheric asymmetry, even if we look like fools, because we got the thing wrong. Well, along comes Scott McIntosh and NCAR. And I don't know if you guys take a look at spaceweather.com. Scott McIntosh is a very good friend of mine. I've been teaching his stuff for a while, and Bob, he and Bob Lehman, they're some of the few scientists that actually take terrestrial meteorology tool, their tool belt, and use it and apply it to the sun. And the reason for that is just like the Earth, the sun is rotating, right? And so a lot of the forces that are caused by a rotating, not a rigid rotator in this case, but just a rotating body, a lot of those same forces are at play. So believe it or not, a lot of what goes on in our upper atmosphere actually occurs on the sun too. There are things like Rossby waves that actually help dictate some of the activity just underneath the sun's surface. So it's a very interesting science that these guys are doing. But if you've seen their papers in Nature, and if you've seen, I don't know, by now just a plethora of news stations picking up their work, it's because these guys are the only team that actually are looking at the sun in terms of their hemispheres. And so if, in a nutshell, I'm not going to go to the super details because there's a lot more to this, and that would have to be a different talk. But they put up this graphic on, it's running in a few places, but I think Tony Phillips of spaceweather.com picked it up and tried to explain it a little bit. So I want to make sure that I take just a moment so that nobody gets confused what's going on. What you're looking at here is essentially magnetic field. Okay, that's what the colors are. I labeled this, if you look at the actual graphic, you won't see this line at 0 degrees. This is, we're talking about latitude, and you won't see northern and southern, but I put those on there to try to make things a little bit easier. And what you're looking at is you're looking at magnetic field direction. So polarity of the magnetic field. Blue is one polarity, red is a different polarity. It doesn't matter which is which, but we can say, if we want to say that red is plus and blue is negative, that's fine. But as you notice, when you get really close to the equator, first of all, you notice that both hemispheres are the opposite polarity at any one time. Whatever's blue and is moving toward the equator in the north, there's red moving toward the equator in the south. Okay, there's that symmetry, right? Notice that as you get one color bar coming down, this band, we're going to call it, coming down to the equator in the north, you're getting a band moving up to the equator in the south, and they're of opposite color. What happens when magnetic fields of opposite polarities touch each other or get close to each other? They begin to annihilate each other. That's why you're seeing the fading out of these bands as they get to the equator. Believe it or not, this is how the solar dynamo works. And in an ideal world, both hemispheres would be doing this exactly at the same time. So you generate from the pole, you generate the main band up in this region. Okay, you have a polar, and that decides the polar cap, basically the polarity of the polar cap decides what band is being formed at really high latitudes up here. See this? So you see the band appear. If it's red, then it goes blue, then it goes red. Okay, then the thing starts over again. And as that new band forms, it begins to go down. There are forces at play that have to do with circulation. There's what we call a meridional circulation that actually pushes this magnetic band down toward the equator. Same thing in the southern hemisphere, it just pushes the band up toward the equator. Well, because they're the opposite polarity, they begin to annihilate each other. But if you don't get, unless you get these bands that are coming toward the equator, until they completely annihilate each other and disappear, the new bands can't move. They can't start their process, the next process of moving down. They have to wait for these bands here at the equator to stop, to annihilate each other. Now, what you'll hear over and over again is when that process happens, when those bands annihilate each other at the equator, that's called the Terminator. Okay, so if you hear people talking about the Terminator, that is what the Terminator is. The reason why it gets complicated is sometimes the band in the north and the band in the south aren't coming at the same time. One is a little ahead of the other. In this case, in the recent case, the southern hemisphere has been faster than the north to come down. So the southern hemisphere gets all of its magnetic band annihilated before the northern does. And so it makes this delay in when the Terminator hits, because you have to get all of the northern band annihilated as well as all the southern band annihilated. And that's what we're looking at on this side. Now, I probably won't go into the butterfly diagram here because that gets a little complicated, but I'll just take the time to do this. I can do this in a question and after period if you'd like. What you're looking at is what you've already seen, sunspot number. Okay, here's sunspot number going up from 0 to 250. Here is time. Okay, this is solar cycle 24. This is a cycle we just finished. The black line is the number, is a line that you're used to, right? You see the double hump. The blue and the red lines are actually what the sunspot numbers look like for each hemisphere. In this case, I believe, let me take a look. Well, this is, I'm sorry, this was solar cycle 23. This one's solar cycle 24, my fault. This is the one we just finished. And blue is north. So the blue line was the northern hemisphere in this last cycle. And notice it peaked last. And red, that was the southern hemisphere. The red hemisphere actually peaked in sunspot number first. So what that means is that the southern hemisphere got to solar maximum and then the northern hemisphere did. So it's like I talked about. We don't have an overlap, we have them side by side. That stretched out the solar cycle and made it a little bit longer. It gave us a double peak. But the funny thing is that the southern hemisphere, which peaked earlier, it now has gone to solar minimum, boom, a lot faster, whoops, than the north has. And what ended up happening is that because we've been waiting for the northern hemisphere to finally zero out its magnetic field, that's when we'll hit the Terminator. That's when we'll start taking off. And anybody who's seen the sun, they'll notice over the past few months, the southern hemisphere has always been generating far more sunspots and far more activity than the northern hemisphere is. But finally, it looks like the northern hemisphere is getting there. So this is what's made the news in terms of Scott McIntosh and all of that stuff about the Terminator, about how sunspot cycles actually work, and why we've had such squirrely sunspots or squirrely solar cycles over the last 2 or 3 or 4 of them. It also explains this, which is from solar cycle 19, outside of which was the big cycle that everybody remembers. Okay, that was back in the 50s and 60s. We had solar cycle 20, which was a little bit of an outlier. It was a little bit quiet. But since about cycle 21, we've been going on a downward decline. This is the grand solar minimum everybody's been talking about, okay? Because we're looking at a plot, once again, of sunspot number. I'm not changing the kind of plots we have. Now, the consensus prediction is that solar cycle 25 is going to be low right here. But this gray prediction, this is what Scott McIntosh's crew has been said the sunspot solar cycle should be. And that is what's caused such a great hot debate in terms of where are we now in the solar cycle transition, is that we actually have a lot of competing cycles competing theories of where the cycle is going to be. The consensus that you see with the Space Weather Prediction Center is that blue line. But Scott McIntosh is both the red dashed line, which I think he's decided is not going to happen, but the red solid line. And that's the one that we've been looking at. Now, the green line is just if you add up all the cycles and take the average, what has solar cycles look like from the beginning of counting, right? So this is solar cycle 25. What have the previous 24 looked like if you just add them and average them all together? So you can see even the average, just the average solar cycle is much higher than the consensus. So I can imagine as amateur radio operators, you guys would be very interested to know if it's going to be the UCAR NCAR group prediction or if it's going to be the Space Weather Prediction Center prediction, right? Because you'd probably love a cycle that is basically the largest since solar cycle 19, and you'd probably hate having one this low. So I know a lot of people are paying very close attention. And if you actually look at the most recent numbers, because all this is a blow up of this early phase here with all these numbers in here. Okay, so all this leading edge. So all the colors are the same. So here's the early prediction. And back in November, it really looked like we were actually going to maybe get this dashed line where we was going to actually have a maximum maybe by as early as 2023. But since then we calmed back down. This is again sunspot number, and you're looking at the average number. But we've picked up again. And you can see the latest sunspot numbers are sitting right about in here. And even the average, if you look at the kind of like this little purple line that's trying to smooth out the sunspot number, I think that's the monthly smoothed number. It looks like we're still picking up a bit faster than what the consensus is. And the consensus is this purple line here. So we're keeping an eye on it, but there's a chance that we're either going to look like the average solar cycle, which will be bigger than cycle 24, or even Scott McIntosh. We're still on with their team. We haven't been able to say no yet. So it's a very interesting cycle to be looking at this. And yes, for those who thought when we jumped up to 110 in the sunspot number back in November, yes, we can jump up that fast. Because if you notice prior to that, I know I'm standing in the way of the scale here, but back late last year, we were hovering around between 70 and 75 for solar flux. And within literally 2 weeks, we went from 75 to 110. So can solar flux rise that quickly? Yes, it can. So when the sun finally decides to turn on, it will turn on very quickly. And there's that peak. And you can see it both in sunspot number here and in solar flux. They really mimic each other. So when you see those sunspots jump up, you will see solar flux jump up. And yes, you can go over 100% that quickly. So how does that affect the upper atmosphere of our Earth? Well, just like I said, the sun has its own plasma, right? It's a gas that's charged. The ionosphere is the same way. That's our upper atmosphere, but it gets charged by basically the sun's ultraviolet light. And of course, this charged nature then makes it behave, it makes it be ordered by Earth's magnetic fields and electric fields, but then it also facilitates radio propagation, right? And oftentimes during active space weather, the energy that gets caught in the Earth's magnetic shield gets funneled down into the upper atmosphere, and that causes the aurora, as you can see by this here. So the nice thing is that space weather can help, but space weather can also complicate a very complicated picture, because this upper atmosphere also gets affected by weather patterns from below. So it can be extremely difficult to deal with. And if you're curious about ionospheric layers, well, here's maybe a slightly different way of looking at them. Of course, we've got the day side ionosphere and the night side, and we know about layers being, different. Sorry, my video seems to be jumping. I hope it's not jumping for you guys, because it seems like it's jumping for me for some reason. But you're used to, I'm sure, the day side ionosphere and the night side ionosphere, and you may not have seen plots like this before, but really what we're talking about is electron density. So you can see electron density plotted down at the bottom here and across the bottom on same thing on for the night side. And what you're looking at here is just the trace in black line. You're looking at the trace, and where you get the layers actually is simply where there's a peak in the electron density in the upper atmosphere. Well, why would there be a peak here and then a trough and then a peak and then a trough? Why would that happen? The reason for that is because there's competing processes, right? The sun is always trying to ionize. It's always trying to split these neutral particles or molecules into, and atoms into, the positive and negative, right? They're trying to rip the electrons off essentially. And that always happens through, the EUV and sometimes X-ray flux. But at the same time, the particles are banging into each other and they're always recombining. So you have this battle between ionization, what we call ionization, and recombination. And depending upon the species, as you go up in altitude, which is what you're seeing on this axis, okay, as you go up in altitude, not only is the density changing, so the number of particles is getting fewer as you go up, right? But also the species are changing. So oxygen, there's less oxygen, there's less nitrogen, there's less, there's less of certain species relative to others. And so as that chemistry, that atmospheric chemistry changes, there will be natural heights in the atmosphere where, in this case, ionization is winning. And if you get to a trough, well, recombination is winning. But then, the density, as you go further up, the density is changing, the species are changing, and once again, ionization wins. Well, you keep going up, the species are changing, the density is changing, and now recombination is winning. And eventually, you keep playing this battle over and over again until eventually the ionosphere gets so rarefied, meaning so few particles, that they just don't hit each other anymore. So recombination can't win anymore. It's done. And then you just kind of fall off over time because you're just so rarefied. You're basically in space at that point. So obviously in the day side, where you have the sunlight creating all this ionization, it's going to be a lot more complicated than the night side, right? At night side, recombination wins mostly. And that's why the layers really kind of fall apart. And you get a lot of sporadic E, not so much but due to space-based stuff, but through terrestrial weather. Believe it or not, terrestrial weather adds a lot of this with sporadic E, and so do things like meteors. So different roles play different things. But as you can see, a lot of the layers, the D layer disappears completely. The F1 and F2 layers combine. So this is kind of a neat picture. It gives you a nice overview. But there's one thing wrong with this picture, because it shows that there's just this line between day and night. There's really only 2 regions, but in actuality, there's 3. The reason for that, and we call that the gray line, it should be called the gray region, not the gray line. And the reason for that is because it's really, that's the day-night terminator, which is not the same thing as the sun terminator. The day-night terminator is really a line on the surface of the planet. But as you go up in altitude, it's just like when you're let's say if you're down on the ground and you're watching the sun is just set for you, but you look up in the sky and you see an airplane flying by and they're still lit by the sunlight. The sun hasn't set for them yet. Same kind of thing as you go up in altitude. The higher you are, the longer you see the sun, right? Because you can see further over the horizon to where the sun is. So it's the D layer, which is the lowest layer, that dies off first. It loses the sun sets for it. And then the E layer sets a little bit further back. And then the F layer, F1 and F2. So as you can see, this, if the sun is setting for F2, clear back here, whereas for the D layer, it's clear over here. Well, that gray line is no longer a line. It's a region, right? And funny stuff is happening all through this period at different heights in the altitude or in the atmosphere. So that's one of the things about the gray line, is that people think that it's just a line, when in actuality, it's a region. And I always found this plot to be extremely useful, because this one always, it shows kind of, it's a simplistic version. It just shows the F layer. It's not showing F1 and F2 for the day side, but it's showing the day side. Of course, it's showing the night side, but it's also showing how things are rapidly changing when it comes to the gray region, right? And you can see the D layer falling off first, so that what was, your top bands, right? 160, 80, and 60 meters, useless during the day. Well, that D layer dies off as you go through the gray line. And at nighttime, now you can use them, right? The E layer also dies off, and the F layer not really comes down in altitude, but in terms of its increasing skip frequency. So what's nice is that, now you can easily, I love this plot because it lets you easily see that you can use, 80 meters at night, but you can't use 20, at least not very well, maybe during solar maximum. But it also lets you know that the gray region is definitely a region, not a line. And there are actually 3 different regions when you think about radio propagation. Now, of course, there's also space weather effects. And space weather effects, really, terrestrial weather effects and space weather effects actually make these layers, instead of being nice, pristine, smooth little lines, they actually are real, wavy, because you've got things like atmospheric heating instabilities from below. You've got things like what we call plasma bubbles. You've got, you can get signal reflection and refraction. This causes major problems for things like GPS, because you've got currents in these charged regions. You've got neutral winds as well as winds in the ionospheric, in the charged regions. This can cause signal scintillation. Scintillation is like, everybody knows what it is, even if you don't know the word. It's twinkle, twinkle, little star, right? You ever look at Twinkle, Twinkle, you see the city lights in the distance and how beautiful they are at night, or you look up at the stars and they're all twinkling. Believe it or not, that's scintillation. But that's visual scintillation. It's using light waves, from the visible range. Well, sadly, same thing happens if you're under aurora, or if you're during a big solar storm, a big geomagnetic storm on the Earth's night side, and you have these big problems going on, and you're getting the ionospheric layers being all messed up like this, you're getting signal scintillation. It's beautiful to watch in visible light, but you sure don't want that for your radio signal, right? That's when you get, all that phase, phase issues you get, and you get, if you're doing GPS, you get loss of lock, or you get fading, signal fading, and all that other kind of thing. So this is the complication when it comes to space weather. And believe it or not, it gets even more complicated than that. I mean, it's an incredible dynamic ballet because you have all these different processes, and trust me, there'll be a test on this tomorrow. So make sure you memorize it tonight. Okay. Because that's, this is easy, right? You can do this in overnight, no problem. You get a lot of different processes coming in from above, and it includes particle precipitation. It includes waves and other types of dynamics. You get this funky slingshot effect that creates the aurora. Then you get all these currents and other different types of phenomena, micro instabilities happening. And then from below, from underneath the upper atmosphere, you get all that terrestrial stuff. So you get stuff propagating up from underneath, causing that the ionospheric layers. If you think of the neutral atmosphere as being like a waterbed, and you think of the ionosphere sitting on top of that waterbed, then you can imagine if that waterbed is all wavy, whatever's sitting on top of it is going to be all wavy too. And that's kind of what it has to deal with. So the poor ionosphere is like a person laying on a really wavy waterbed and getting rained on from above. And that's where it becomes this cookie, the cream filling in an Oreo cookie. It's just being squashed from both sides. And that's why radio propagation is so incredibly complex, because you get all of that stuff from both above and below. And remember, the Earth is rotating. So you're going to have a day-night, a day side, a night side, and a gray line to deal with. And it's always changing. So for a long time ahead, we're still going to have problems understanding radio propagation in many different frequency ranges. So for those of you who like to try to do space weather or predictions for radio propagation, really things like, the reverse beacon network, for the Whisper network, PSK reporter, those things are still the best way to try to probe the ionosphere in real time, because we just don't have a decent way of predicting it as quickly as things change. Now, before I move on, because I can give a few examples, or I can kind of stop here. I've got like one example that I was going to show about space weather storms, but I want to probe everyone to see how everyone's feeling. Because I was going to show the example from 2017. If you guys remember Irma, Irma and Marie way back in 2017, when we had some really bad, those really bad hurricanes and a lot of first responders having issues. Does anyone want me to continue that, or should I pause at this point?
How about a show of hands to continue? All right, I'm seeing a lot of hands. Yeah, I'd say go ahead and continue.
Okay, I sure will. So I have, I'm just going to really show this one event. I'm going to give you a tiny bit of background on it, just from the point of view of the Space Weather Prediction Center, because I don't know how many of you are familiar with the Space Weather Prediction Center scales. Yes, I know you can't read this, don't worry. I do have a link on this side, so if you guys want the PDF version, it has a link on there where you can go to get these Space Weather Prediction Center scales. The only reason why I've got them listed is because I'm going to refer to them. There are essentially three categories in the NOAA space weather scales. You've got the G scale, the S scale, and the R scale. The easy thing is that they all just go to 5, just 1 to 5, okay? The G scale is for solar storms, right? The big coronal mass ejections I talked about. Those are the big slow moving things, that belches of stuff from the sun that reach Earth and cause aurora and cause radio propagation issues on Earth's night side. For those of you who are used to data products from SWPC, this is what you would look at KP for. And sometimes A, but A is really not a savvy thing to use if you want to know what's going on right now. But that's what a KP index is used for. So that's the G scale, okay? We also have the solar radiation storm scale. That's the S scale, not the R scale. That's the S scale. Sadly, it's a little confusing, even to me to this day. That's when those radiation storms, remember we talked about the fireworks in the eyes of the astronauts, and the ones that hit the north and the south at high latitudes and just totally pepper the D layer of the ionosphere, making radio communication nearly impossible. And that can last for days. That's easily lasts as long as it takes the solar storm to reach Earth, because that's actually what's driving it. So that's the S scale. And again, it only goes to 5. And then there's the radio blackout scale. That's the R scale. And this is when the solar flares hit, right? This is the sun screaming. It hits you on the day side only. And it hits you typically only for a couple hours, if that. sometimes a lot faster, just for a shorter period. It all depends. But again, the scales only go to 5. Okay. So those are the 3 scales. And the reason why I wanted to show them was because it will help kind of calibrate you for this next event. And because I'm not going to show what a typical solar storm can do, or a typical solar storm event series can do, I'll just let you know that a typical solar storm event series will be around, let's say, a G2 to a G3. It could be a G1, but that's pretty mild. A G2 to a G3, remember the scales only go to 5. An S1 to S2, okay? And an R1 to R2, probably R1 to R2. That's what a typical solar storm series can do. And those happen during active times. Those can happen once or twice a month. We get them a lot, believe it or not. And you'll start noticing that over the next couple of years because the sun is getting active. But let's talk about this particular event. Anybody remember Irma and Harvey and Marie back in 2017? Hopefully nobody had to work it. I remember giving a keynote lecture to the Southwest, I think the Southwest chapter of the ARRL here in Los Angeles. And it was like in November of 2017. And I asked how many people were working it, and the whole room groaned. They hated it because the nets were just so bad. It's so hard to work. And there was a lot of need at that time with Puerto Rico going down. So here's what happened, right? Back in end of September of 2017, this is what Houston looked like. It was underwater because Harvey had just drowned the poor thing. I mean, it was a storm. It was essentially a hurricane-like, and it just lingered for so long that it just dumped tons and tons of water. And here was a newscast. This poor gentleman, I don't know if you guys recognize what he's on. He's talking here. If you see this antenna, you can tell it's not a typical cell phone, right? This is a satellite phone. And what happened here was that this poor teen, he was like 18 years old, he had never been through a hurricane, and he had come to Arlington looking for his dad, and his cell phone was out. It had run out of power. Besides, it wouldn't have mattered because all the cell towers were down. There was no power to charge anything. There was no other way to call. And he drove to where his dad's house was, and the house was totaled. I mean, it was just gone and nobody was there. And he was freaking out. He says, there's trees down everywhere. I can hardly go anywhere, and I don't even know where my folks are. He happened to run into this reporter. And this reporter, of course, was covering the storm, but he had a satellite phone. So the reporter actually covered when he let him use his sat phone, and the boy was calling his dad. As you can see, he's even injured. He had gotten bandaged up because of something that happened to him during the hurricane. And so he's covering his face right there because he was crying. I mean, if you've seen this clip, it's just gut wrenching. And this is the reality, right? When we have these big storms, is that everything gets knocked out. And the sad thing is that everybody, all of the terrestrial meteorologists were, of course, they had their eyes glued to the Gulf and to the Atlantic, because we had 1, 2, 3. I mean, the storms were just coming in, right? Because after Harvey was Irma. Irma was already building, and it was already getting close to Puerto Rico. The sad thing was that while these terrestrial meteorologists had their eyes down on with the satellite imagery down at Earth, watching all the clouds, us solar people, us space weather people, were watching the explosive growth of this region right here. Within 3 days, this region emerged, and it looked like not a great sunspot. Now this is in color. These are color coded. So really, what you're looking at magnet. We talked about polarity, right? So much with the sun is all about magnetism. So blue is coming out, red is going in, or vice versa. I always forget which way it is. But what you don't want, just like with the bands on the sun, is you don't want magnetic field of opposite polarities coming near each other. So if you see blue and red close together, that's bad news. That's unstable, because what happens when they come together, they annihilate each other. What they do is, it's called reconnection. They completely disconnect, reconnect, and let off this massive explosion, which is a big solar flare, and likely launch a big solar storm along with it, and a radiation storm. A lot of this stuff happens all together. So we watched this region emerge very, very quickly, and it didn't look all that great, but it went from blue, essentially a red and a blue spot, to, in 2 days, something that went, if you can see it here, red, blue, red, blue, red. And us space weather people were going, oh my God, This is a Carrington class maker. This is a massive X-flare maker. And sure enough, in a single week, from September 3rd to September 10th, region 2673 fired 4 X-class flares, including the 2 largest of the solar cycle. These were an R3 to R4 level radio blackout. Okay, remember the scales only go to 5. It fired over 25 M-class flares at an R1 to R2 level radio blackout. Okay, again, the scales only go to 5. It fired 2 solar radiation storms at an S2 to S3 level. Again, the scales go to 5. And then 2 geomagnetic storms, one of which was at the G4 level. The scales only go to 5. Okay, this happened in a single week. Okay, that's what happens with space weather, is when you get a bad actor on the sun, meaning a sunspot that's angry, it comes up and it's mad. And it fires off an X-class flare, and it fires off a solar storm, and it waits another minute, and then it fires off another, and it fires off a radiation storm, and it just keeps firing. It does not stop the entire time it takes for that region to rotate off of the Earth-facing sun. Until that region disappears behind the sun's far side, that thing will keep firing stuff at us. And it's just an onslaught. In fact, in this case, it fired the second largest flare, X-class flare, of the solar cycle while it was behind the sun's west limb. So in other words, it had already rotated out of view. We didn't see the spot anymore. We still saw the flare. This was an X8.2 flare, which means if this was already partially blocked, the actual flare was much, much larger because the sun was already blocking part of it out. Okay. Along with this flare was a Carrington class event that it launched. What that means is that it launched a type of solar storm that is the biggest. It's in the same class as the biggest we've ever seen. The kind that you heard about in 1859, the sun launched one of it when it fired this flare. And it was so intense that imagine if I had a gun, okay, now I'm pointing it away from you, you're Earth. Here's the gun that was that sunspot, okay, that active region, and I fire that gun, but the bullet is so wide that it's so wide it still hits you. The edge of it is that big. As it fires away from you, the thing is so big it wraps around and hits you. We got hit by the storm, the Carrington class event that was fired here. It just barely nicked us, and it gave us a G1 level storm. This other G4 was not a Carrington class storm, but it had happened. We got the direct hit from it. So imagine, this wasn't even as big as the other one it fired. So imagine if we got hit by the bigger storm. So this was a nightmare for for emergency responders, because we had DRAP models that looked like this all the time. We had solar flares, which is what this is doing. We had radiation storms, which is the high latitude stuff in red, at both the north and in the south. So we had stuff happening on the day side, right? We had stuff happening at the poles. And we had geomagnetic storms that were hitting us at the Earth's night side. There was no safe place on Earth to do radio communications. In fact, as we take a look at this is, I think, this is either 12 or 24 hours, I can't remember which, of X-ray flux. And you can see this is the R3 level right here. Okay, the radio blackout R3 level. You can see we actually went down. We'd have an X-ray, an X-class flare right here. And then as it went kind of decayed over either 6 or 12 hours, this is probably 12 hours worth of data, we'd get down to about the M1 level. So the M, like an M flare level, right where we just barely get out of radio blackout, and there'd be another X flare. And it would shoot us right back up into an R3. And this happened for nearly this entire week. Okay, this is September, September 3rd through the 10th. So you just never got a break on our stay side. In fact, Aurora, there was Aurora clear down to Arkansas. This is what Aurora looked like in New York. Like I said, we had Aurora down to Arkansas, but I just like this picture, so I show it. This is what Brazilian TV looked like. This is direct TV in Brazil. I don't know if you guys can read Spanish, but it's there was no direct TV signal because of la irreferencia solar. No satellite transmissio. I have no idea what this is. It's like Portuguese. It didn't even look like Spanish, but this was Brazilian TV. This is the reverse beacon network. And everyone knows CW, right? You know Morse code. It's the most robust of all signals, maybe other than maybe FT8, but it's pretty robust, right? Because it uses such tiny bandwidth. Notice the day side of Earth, nothing. And if that doesn't drive it home, oh, why didn't you let me open it? I'll see if I can open it later. Well, that's weird. Okay. Maybe I can do it. Yeah, open. Why do you need other permission? Boy, that is weird. Why are you doing that to me? You did not do that before. Okay, good. Here's a movie. Let's see if I can make it bigger. This was given to me by GI7ZU, who is running from the UK. He showed me this really cool movie of a lot of radio transmission or radio frequencies. You can see the different colors are different frequencies. And as you can watch, you can actually see the Terminator coming over, but look at this. Right there, pause. This was September 10th. Notice how on the day side, okay, remember we just saw all those different frequencies all over, but if you can see the Terminator here, here's the night side. Look what happened. There's nothing on Earth's day side. And Irma was right about in here. Or my hand in the right place. It was in this area. It was just moving past Puerto Rico and beginning to come up to the Florida Keys. And there was absolutely nothing on Earth's day side. And that was due to that big X-class flare on September 10th. And sadly, I ended up giving a talk to the National Weather Service. They asked me to give an invited talk, I think a few months after the events of 2017. And I shamed them because I showed them this. I actually showed them the actual video too. But nobody in terrestrial weather here in the United States picked up on the story. But a state-run network called REN TV, I don't know if you notice, everything's in Russian. This is REN TV. This is a news anchor, and he's talking about the sun. See, he's talking about the sun. He really wasn't talking about the sun. He was talking about the Hurricane Irma that was destroying Puerto Rico. But he had a bunch of solar physicists on, and they started talking about how space weather actually was making it extremely tough for the emergency responders to do anything, including amateur radio operators. And then the most amazing thing happened. He pulled up my video from YouTube. As you can even see my space weather woman logo that they've cut off. They cut off in the video, but they put on my name in Russian. I don't know if you can see Tamitha Chob. And they had me come on, and they had me full screen, and I was talking about what the amateur radio operators should expect and how they should deal with it, and where they should try to get their winds where they could, when the day side would be good, when the night side would be good, and how to deal with it. And they played that section, and they played about 3 seconds or so of my actual English, and then they had the translator come on. So I got to hear my very first space weather forecast in Russian being dubbed by this meteorologist who was actually doing the weather for the Russians. And they were just showing pictures of what Irma was doing and what other hurricanes could do. So I ended up showing this to the National Weather Service folks, about 200 meteorologists, all television meteorologists in a room. And I shamed them all. And I thought they were going to pelt me with olives. And what happened after my talk is they all wanted to buy me a drink. We were all in a hotel. They all brought me to the bar and sat down, and I got like 3 or 4 different beers. I couldn't even drink them all. I had so many. But it was really, really cool because they were so interested in this aspect of weather that they had never really ever taken into account. And they were seeing the relevance to their lives. So that's really the take home when it comes to this stuff, is that that's really what I'm trying to do. That even though we do have space weather prediction centers all over the globe now, I mean, they're getting more of them all the time. A friend of mine's just now starting one in South Africa, believe it or not. He's going to Sansa, and he's going to stand up their weather center. And he's from Colorado, basically from not the Space Weather Prediction Center, but from University of Colorado in LASP. So I'm going to help him try to stand up the one in South Africa. But they're getting to be more of them. But they're all based on models and things from academia. right? They're all based on scientific stuff. So a lot of these people are from that industry. They're not meteorologists and they don't really know the field yet. And Matt Parker, bless his soul, he was the president of the American Meteorological Society. He told me, I reminded him of Harry Volkman. And for those of you who might know the Chicago, the Illinois area, he was a broadcast meteorologist who was the very first one to actually take, he was also an amateur radio operator, and he took space weather forecasts that the military was giving, was basically tornado warnings. And he would listen to them in CW, right? Because he'd translate them because he was hearing them. He was basically overhearing them being given to a military base. And he'd take them and he'd then broadcast them on terrestrial, on TV for his audience. And a ton of people said, oh my gosh, you can't do this. You're going to incite a panic. And believe it or not, he didn't. Instead, the very first time he did this, he got something like 1,600 letters of thank you. We appreciate so much what you're doing. You are making our lives so much better. We feel so much more informed. Keep doing what you're doing. And Matt Parker told me, he said, Tamitha, you are like the Harry Volkman of space weather. And the funny thing is, he was right, because I get the same kind of thing. I have a ton of people from the military, from my bailiwick, from academia, telling me, you can't talk about this stuff. You're going to incite a panic. People are going to go crazy. This is really not meant, space weather is not meant for the normal, the average person. And I'm taking a page right out of Harry Volkman's playbook and saying, yes, it is. Yes, it is. I'm banking on the fact that people want this information. Otherwise, they wouldn't be asking it from me. And that they're not going to panic, that they're going to feel more informed, and that this is going to be the weather of the 21st century, really. So that's really what I'm trying to do. And as we advance so much more in space, oh my goodness, we can't have weather people who are saying things like this, like solar flare races toward Earth. And no, a solar flare would have hit us in 8 minutes. What's racing towards Earth is a solar storm, not the solar flare. The solar flare gave us the radio blackout. What's racing toward Earth now is the solar storm that came with it. And that's going to cause, radio propagation issues on the sun, on the Earth's night side, not the day side. We need to make sure that those types of things are clear. And so we can get reliable space weather forecasts to help out everybody. So for those of you who know me, that's what I do. And that's the field I'm trying to create, is space weather broadcasting. So we can train meteorologists to do it the right way and be of service to people like you, right? And people like me. And that's pretty much it. If you want to find me, I'm very easy to find. I'm all over the place. So please reach out, and hopefully you enjoyed the talk.
Thank you so much, Tamitha. Are there any questions? If you could raise your hand, and we will recognize you. I'm looking for hands. Any questions? Norm, do you?
You're probably all tired and want to go to bed.
There's Phil. Phil, unmute, unmask, and ask your questions.
Thank you, Brad, and thank you for the presentation, Tamitha. Curious which way the ARRL is going. I know that you've been working on some curriculum changes, and you were asked to do that because the ARRL wants to change our understanding of space weather relative to our hobby. Is there any way that involving us through education, through the ARRL, we can become more valuable to the community of scientists as amateur scientists or as data collectors? I mean, we're sitting here with the tools to communicate rapidly information and gather information. We do it for earthquakes. We're doing it with WinLink. We're doing it with all the tools we've got. Is there anywhere and any place for us in space weather?
Yes, absolutely. As a matter of fact, as you might know, as some people do know, I am working with the ARRL right now, along with Nathaniel Frizzell, who is the leader of hamsci.org, and that is, of course, is a citizen science, an amateur radio citizen science community that has been doing some amazing work and huge leaps and bounds in terms of ionospheric science. As a matter of fact, I'm trying to get them to create some real-time data products so that we can at least do nowcasting of the ionosphere through actual probing of the ionosphere, through radio contacts, because the data is out there and it is available. It's just a matter of being able to process it in real time. So that is something that is definitely coming. As far as working with the ARRL and in educational materials, Nathaniel and I right now are working with Steve Goodgame and a few others, Bob I can't pronounce his last name. I'll completely butcher it if I try, so I won't try. Sorry, Bob. But they, as a group, we're actually creating a primer for them. We're actually in the process of creating a storyboard that we're going to start recording here in the next probably month. And we're going to be talking about basically radio propagation from mud to sun. We're actually going to be working from the ground up instead of doing what most people do, which is talking from the sun down. So we're trying to put it in more of the perspective of an amateur radio operator. And we're literally going to be talking about everything from terrestrial weather on up to the sun's, the solar cycle and how it is affecting radio propagation, to try to give a much more realistic understanding and education to not just new amateur radio operators, but the seasoned vets as well. And after we're done doing that primer, then we plan to do other modules that will break out in more detail some of the stuff that we kind of gloss over just a little bit. So this may be an ongoing process that we're doing over the next, I don't know, maybe year or two. And definitely on our way to solar maximum. So we actually do have multiple things moving on multiple fronts. But I would say, as far as getting more involved with amateur radio in terms of doing citizen science and how you can help out the scientific community be better at predicting radio propagation, get involved with HAMSci, because they are literally leading the charge. And the nice thing is, it's finally making some of the people in the academic community swivel their heads over and take a look, going, wow, I never knew that people could be rallied like this. And they're beginning to see that, not just with HAMSci, they're seeing it with Aurorasaurus. As a matter of fact, I brought those two groups together so that we can create these space weather stations. And HAMSci is taking the lead on that, but we're going to have Aurora cameras. We're actually having magnetometers on these space weather stations. And once they get into mass production, because they're still working with the Raspberry Pi, there's two different flavors of the station. There's a more scientific one, and there's a little bit more of an amateur one. And they're at different price points. But we're hoping to deploy these. And as we start getting people who want to deploy these and be buckled into, let's say, the Whisper network as one example, it will make it much easier to do these soundings of the ionosphere in real time and get the data to scientists to be able to make new models. And we probably will start making new models of, and be able to compare them with a lot more of the space weather indices and the local magnetometers and things like that we already use. So it will be a massive change in how space weather is done. At least operational space weather is going to be done over, I say, the next 5 to 10 years, over this next solar cycle. Hopefully that answers the question, Phil.
Yes, thank you.
And thank you.
Howard, you have a question.
Yes, it seems obvious from Tamitha's display when she was talking about the Irma. The question I came up with, is there a correlation between terrestrial weather and space weather?
You know what? There are certain correlations, and we don't know them very well. And part of that reason is, as you could probably tell from just the information I gave you here, my goodness, you could get a PhD in any one of these different disciplines. So you could just stare at the sun all day and just get a PhD in that. You could stare at the Earth's magnetic shield and get a PhD in that. You can stare at the ionosphere and just get a PhD in that. So everybody is very compartmentalized, sadly, in their respective fields, and there's not a lot of cross-pollination. But that is one of the things I'm desperately trying to do by getting terrestrial meteorologists involved and trying to get cross-disciplinary studies between space weather and terrestrial weather. The little bit of studies that have been done have been mainly on things like cosmic rays, how cosmic rays are seeding clouds. We do know they seed clouds. How well they do that, it's hard to say. It looks like they're also affecting noctilucent clouds. And this recent solar cycle, because the cosmic ray flux, like I said, during this last solar minimum has gone higher than we've ever seen. We're actually seeing noctilucent clouds much further south than we've ever seen them before. And we believe that there's a correlation with cosmic rays. So that's one. Another one is lightning. There have been multiple studies done now from multiple different institutions that have shown that lightning in hurricanes seems to be intensified when there is a solar storm raging. Now, some people go so far in fringe science, they go so far as to say, well, solar storms cause it. No, they don't cause hurricanes. But could they intensify something that is already there? Yes, it's possible, especially when it comes to the electromagnetic coupling. But we don't know enough about the atmospheric chemistry, and there's not been a lot of people who do basically the electric, the charged atmosphere and the neutral atmosphere and how all of that couples in together. It's a very complicated chemistry that goes on, and it's not just electricity. There's a lot more to it. But yes, there is that side of things too, and much more interest in the meteorology community is ramping up because they're beginning to see some of these correlations. At least a few of them are, and I'm hoping that's something I'm hoping to change as well as we move through this new solar cycle. Hopefully that answers that question.
Orv, you have a question. Are you there, Orv?
We can't hear you.
Okay, we'll come back to you. Keep working on it. Gary, you had a question.
Yeah, you can hear me okay?
We can.
Yeah, Tamitha, good talk. Point of reference on your data, you showed several images of the sun of different colors. And my understanding is that that's different wavelengths produced from the photosphere, right? Is that correct?
Not all. It's not all the photosphere. The photosphere, the photosphere of the sun will be, let's say, 1600 angstroms, right? Because now you're getting into the chromosphere. When you get into the EUV range, the extreme ultraviolet, like this, like the red, that's 304 angstroms. That's the chromosphere. So that's above the photosphere. Okay. And then as you start moving into 211 and higher, you're getting actually into the corona. Okay. So you're getting even above the chromosphere.
Okay.
So
because
no,
go ahead. I'm sorry.
Yeah.
Well, my point.
That's
okay. Because my point is that as astronomer, as an amateur astronomer, what I do is occasionally I'll use the hydrogen alpha line and use a telescope to monitor the chromosphere. And you get quite a bit of information as far as the granularity of the sun's surface, where the sunspots are going to be. You can see solar flares, of course. And so for ground-based looking through the atmosphere, that's a pretty good means of looking for activity on the sun. And then what I personally do is combine that with stuff like that comes from Mount Wilson. And you get a pretty good idea of solar activity beyond looking for X-ray or UV or whatever else.
Right, but you won't be able to predict, for example, when fast solar wind is going to hit, because you'll never know when a coronal hole is coming. Right, so you won't see a solar storm. Like, for instance, the solar storm we just had over the past 48 hours, you would never know that because you would not have seen it. You also don't get to see these loops. So you don't get to see how large a coronal mass ejection is or what direction it's moving. So you may see where a solar source is if there's a solar flare, but you won't necessarily know if something's Earth directed. You might get a decent idea if it seems to be in the Earth strike zone, maybe kind of sort of, in the Earth facing disk. But a lot of times these big eruptions, when they occur, will shoot off to one side or another, or shoot high or shoot low, or they'll be deflected by, let's say, some fast solar wind from a coronal hole, depending upon the proximity. And then there's also weaker events that don't have any, that really aren't flare related at all. They're just filament channels that slowly lift off and stealth CME-like, that don't have any low coronal signatures, and you would have no hope of knowing that they were coming.
Okay, so what
Those
wavelength?
invisible ones are problems.
Okay, what wavelength is the best to see a coronal hole? Is that in the X-ray?
A coronal hole?
Yeah.
That'll be. Yes, you can actually see, you can see it if you, well, first of all, we don't have an X-ray imager anymore. I mean, we have SXI, but it's pretty damaged. The best way would be an EUV, and it would be in, let's say, anywhere between 190 and probably 211. 190. So that's one of the reasons why the beacon data on stereo is 195.
Yeah.
Because that's kind of like a catch-all. If you run 195 to 200 angstroms, anywhere in there, you're going to be able to get kind of a catch-all. You'll see solar flares, you'll see coronal mass ejections, you'll see filaments, and you'll see coronal holes. So you'll know where fast wind is.
Okay. So what do you think I can see at 658 nanometers? That's hydrogen alpha.
Yeah, well, you're going to see the filaments. You're not going to see any of you're not going to see coronal holes. You're not going to see a
Okay.
direction of a coronal mass ejection lifting off.
I see.
You won't see any of that. H alpha will show you a filament lifting off, but that's not exactly the same thing. And so sadly, the ground-based telescopes are really limited in what they can see. There's only a limited amount of science you can do
Right.
with them.
Yeah.
Sadly,
I agree. Okay.
just that
thanks.
atmospheric window. We're just stuck
Yeah.
with it. Yeah.
Yeah.
Okay,
Thank you.
Orv, did you get your microphone up?
I don't know, did I?
Yes, you did.
Yeah.
Okay. Tamitha, I bookmarked an article a number of months ago out of the University of Colorado's Laboratory for Atmospheric and Space Physics. And it was talking about
Blast.
something called the magnesium 2 index and how it would be a good predictor of radio wave propagation. Can you comment on that? Or,
Oh, I think they were talking about type 3 bursts.
okay.
I think they were talking. Is they talking about type 3 bursts for radio waves?
I don't know. I just bookmarked the article and some cute looking graphs. The SORCE magnesium 2 core to wing index time series. And the article talked about how it was a leading indicator of radio propagation. I'll go back and read it some more.
Right. Yeah. I do believe I know what the article is, and I believe it is. They're talking about type 3 bursts. There are, and this gets really complicated real fast. And you know what, I might actually, hold on. Do I have that plot in here? No, but I have something else. Okay. Now this is not exactly what I intended to talk about, but and doesn't quite address what your thing is. But you know, when it comes to active regions on the sun, of course, you've got things like white light and total solar irradiance. But the sunspots, even though they're visibly dark, as you can see here in this white light image, they're visibly dark. But if you look at them in 1.4 gigahertz, for example, from the VLA radioscope in Owens Valley, you see the sunspots stick out quite a bit because they're extremely radio loud, and they're extremely radio loud in very, you know, in a lot of different frequencies. And it really is not because it's actually coming from the sunspot itself. It's actually coming from the magnetic field loops that overlie that sunspot. In fact, when you look at, in this case, this is Trace with showing the radio contours of, and I forget what, 8 gigahertz, an 8 gigahertz radio contour. You can see this, the highest contours, the source, meaning the most intense, is in these two inner circles, and then it kind of fades off a little bit. So the source, the most intense source of this radio, this 8 gigahertz radio noise, is actually above what is a sunspot on the sun's limb. So if you can see this dark black thing here, see this right here. So really what we're talking about when we talk about radio noise coming from the sun, it's actually coming from the sun's magnetic field. And when you get big solar flares, what happens is that in solar flares and oftentimes coronal mass ejections, is there's this model, there's a standard model where you get this big X line and you get stuff that's being shot off of the sun, and you get stuff that's coming slamming back down to the surface of the sun. And it's particles that are coming, but they're streaming both out and down. And in all of that process, there's a veritable buttload of radio emission that occurs on all these different wavelengths. And you also get hard X-rays. So this is when you get the big X-ray flare, but you can also get microwave emission, literally right at this loop, at the top of this loop, that is a loop you can't see here, but it's above this sunspot. The loop actually has magnetic field lines that go underneath the surface. And so really what you're seeing is a penetration of that loop up through the surface of the sun. And it kind of like a submarine displaces the water. And if you can imagine the water, the surface of the sun being kind of like water that's lit, like water that bubbles up light. If you displace that water by some other body, like a submarine, all that area where that submarine is popping up through the surface is going to be dark because there's no light water all around it. It's dark. It's kind of like a shadow, right? So, and I talk about this in a different talk, but that's really what you're seeing is a magnetic tube coming out, and it's the tube that actually has where the radio emission is. Well, when that thing reconfigures during a big solar flare and it launches a big solar storm, big CME, there is a lot of magnetic field configuration that changes. There's a lot of particles being shot down, so there's a lot of energy being given off, and some of that is coming out in radio noise. As you move further away from the sun, the density of the plasma, the upper atmosphere is changing. It's actually dropping, right? The density is going down as you move further away. It's just like moving up in altitude at Earth, the density goes down. As you go out further away from the sun, the frequency of the radio noise also goes down because it's a function of density. So as density goes down, the radio frequency goes down. As you go and as you launch something, a big coronal mass ejection, out in front of that coronal mass ejection is a shock wave. That shock wave is also a radio noise source. That's where you get the type 3 bursts. Okay, so when you talk about the magnesium-2, which is a good tracer, they're talking about tracing the shock front of that coronal mass ejection as it moves out from the sun. And in the case of an Earth-directed storm, it's the shock wave is moving toward Earth. So a lot of space weather forecasters that care about coronal mass ejections being launched, they look for these type 2 and type 3 bursts. They look for these radio bursts because that means a coronal mass ejection is being launched with a big shock wave. And oftentimes when you get that, you're going to get a solar storm, and you oftentimes will also get a radiation storm with it. So that's why there's all this hype around these types of bursts. The funny thing for me though, and it may be just incidental, but where the academics focus too much on type 2 and type 3 bursts is that they're worried about the coronal mass ejection. Me, I'm more worried about the L-band burst, right? I'm worried about the microwave burst that comes, because that's the sun screaming in GPS frequencies and satellite phone frequencies, right? I mean, and just satellite communications frequencies. Those are the bursts I don't like. A type 2 or type 3, okay, fine, we're going to get a geomagnetic storm, great. We're going to get a big CME hitting us. I don't care. But if the sun is screaming at 1.4, 1.5 gigahertz, I got to warn everybody that their sat phone's going out. If it's at 1.2 or 1.3 gigahertz, I got to worry about everybody's GPS going out. I got to worry about drones flying and crashing into things, right? I got to worry about lots of other stuff that to me is far more relevant to society. So, okay, yeah, magnesium-2, type 3 bursts, type 2 bursts, great. But to me, that's a perfect example of how academia misses the mark, because they're more interested in the phenomena than they are in the impacts. Does that make sense?
Yeah. Wow. Okay. Are there?
Sorry, I don't mean to be too hard on you.
No.
I don't mean to be a little punchy on that, but it's just my angle, just where I come
from. It came from academia, so that's okay.
Yes. Brad, there were two others.
Okay.
Yeah, sorry.
Go ahead and call them, Keith.
Okay, just hands that were raised. The first was Greg, K7SDW.
Well, my question is more, I guess, information in regards to the sensors that I guess that are on the station or the various satellites that are probably used to correlate or to gather your data. I guess is our government or somebody thinking about trying to use sensors be stationed on the moon or even on Mars to do some other correlation that gives us more of a more three-dimensional, if you will. I mean, I think it was with Voyager 1 and Voyager 2, we're picking up some data that they sent back that says, wow, we found something more about our sun's shock wave. I don't know if you could make sense of what I'm asking, but go ahead.
Yes, I do completely understand. And yes, I think there are certain things that we have to worry about. The idea of having stations on the moon would be fantastic. We still, because we could, satellites have what we call swap, right? There's size, weight, something in power. I can't think of the other one right now. But we have to, size, weight, and power, and we always have to worry about how big an instrument is, how much power it's going to use, the real estate it's going to take up, and how much telemetry it's going to cost us. And that oftentimes is a huge limiter in the trade space. So looking at what type of instruments we can have under different payloads. And of course, the cost, that's the big showstopper. So that's why we don't have a lot of chronographs in space, sadly, because chronographs are very big things and they're expensive. And so it becomes a real battle in a totally different realm when it comes to getting new instruments up really anywhere. And when it comes to the moon, there's a new battle, because now if we can get the supplies, then we could eventually build it. That would be wonderful. But now we have to worry about other things like the neutron albedo from the lunar surface. Sadly, where the sunlit side, the same solar rays that hit our atmosphere and cause ionization, they actually hit the lunar dust and liberate neutrons, which is not good for equipment. So there's going to be a whole new battleground of the types of sensors that we're going to have to be able to be savvy in building and being able to have noise rejection that we're not used to in terrestrial environments, or even on space, in space assets. On the Mars, it's another totally different battle there, because when radiation storms hit Mars, they go all the way down to the surface, because unlike our atmosphere, that atmosphere is really tenuous. So because the space weather is so pernicious at Mars, it's a much more violent situation. Mars's atmosphere basically goes opaque to radio propagation and radio transmission during inclement space weather. So that may affect us when it comes to certain types of instruments, and we really haven't even begun to probe that area, that particular kind of environment yet from a space weather perspective. As a matter of fact, only since Curiosity, I think Curiosity rover is the first rover that actually had a radiation detector on the actual rover, and we've learned a ton about it. This is how we learned that any Martian colony is going to have to live basically underground on Mars because of cosmic rays and because of solar radiation storms when they hit. They're pretty intense. So those are, these are some of the dialogues that are really only beginning to happen. But I guarantee you, scientists want data everywhere. And so if there's a way to do it, we're going to make it happen. It's just, how quickly is that going to happen? Probably not that quickly, simply because there's just so many things that get in the way. And we'll likely have a few instruments that we create and we deploy, and then they fail because of some unforeseen aspect of the environment that we just couldn't predict beforehand. So sadly, that is the nature of things. It will be incremental, and I hope it's within my lifetime, but I'm not sure.
Okay, Keith, you said there was another hand?
Yeah, one more. It was also Greg, KG6BRE.
Oh, did we get him at the first one? No, okay, go ahead. Greg, are you still there?
Nope, you're fine, because I was only going to ask Orb's question for him. So it got taken care of. Thank you.
Oh, perfect. Okay. All right. Any other last minute questions? I don't see any. Do you see any, Keith?
I don't yet.
Okay.
Thanks, guys, for staying on so long with me.
Well, thank you,
pretty late, so
it was great having you, and thank you for your time and all your energy and your knowledge.
You're very welcome.
We look forward to maybe a repeat somewhere downstream.
Sure. Let me know what you'd like me to talk about. I mean, there's a lot more to this story, so you guys can have a cool powwow and figure out what you want me to talk about next time. I'll be more than happy to.
Once again, thank you so much. And just as a update here, at our next regular club meeting, which will be Thursday, July 15th at 7 p.m. And it'll be on Zoom, just like tonight. And if you lose the information, it's on the website. The topic will be nano VNA by our own Warren, K6WKW, and he'll introduce the nano VNA and talk about this little tool and its how versatile it is, and surprisingly simple. He's going to make it very simple, and who knows, we might have a club project in the future. Warren, do you want to throw out any little candy on that one?
Well, following Tamitha, I'm going to say probably not so dramatic as the incredible things that she's looking at and doing. But I hope it'll be interesting and informative, and we'll see how it goes. Hopefully we'll stay tuned in. Thanks everybody for being here.
Okay. Yeah, go ahead.
Yes, thank you. Oh, thank you, Keith. I appreciate that. And Philip, I appreciate that. And Brad, all of you guys, thank you so much. You're so very kind.
Thank you,
It was a real
Tamitha.
treat. And I love the questions. You guys are just, as always, you radio amateurs are you're just so savvy. I mean, some of the smartest questions, you really keep me on my toes. I have to really think to answer some of these questions. So I appreciate it very much.
Okay, and one last thing, Tamitha, if you're not doing anything on field day, you're more than welcome to run out to, we're right in front of Sherwood Country Club. It's our location's not quite as beautiful as Sherwood, but it's a beautiful field, and we're going to be having a picnic, and you could be our guest for a picnic barbecue Saturday night. So if you're looking for a field day site, you're more than welcome.
Thank you so much. I don't know yet. I have to figure out what my family's doing. So
All right, well,
I'd like to say yes, but I don't know yet.
all right, well, if it does, you know how to get me. You just contact
Absolutely.
me and I'll get you all the details. And with that, I'll wrap it up and everybody can finish their evening. Thank you so much for being on tonight. And are there any last final thoughts?
Yes.
Did I hear
Thank
somebody?
you, Tamitha.
Oh, okay.
Brad? Hey, Brad,
Yeah, go ahead.
you know what, for Tamitha, hey, Tamitha, if I have one invitation for you as well. I have access to the JWST, and if you want a tour, I can give you one.
Oh, that'd be very
Interested?
nice.
You
Yeah,
interested?
we should. Yeah,
Okay, because Keith,
actually, I am.
okay, Keith is, the other interested. Victor, quick story. I don't want to keep people, but it's in Redondo Beach, if you know, and I have a connection with it. I have actually helped build it, but it's almost
Very
packed.
cool.
Yeah, we built the infrared detector on it, but it's almost packed. They're going to ship it off to French Guiana within like a month or two. So if you're
Oh
interested
my
in
goodness, so
seeing
this
it,
would have to be fast.
yes, you would.
Yeah.
You have to move very quickly. I'm sorry about that. Through Brad, you can get contact information from me if you're interested, but you
Yeah.
got to be ready to move at a moment's notice if you want to see it. So,
Oh my goodness. Okay.
okay. Yeah,
Thank you. I absolutely. Oh, I'd love that. Yeah,
Yeah,
Brad,
yeah,
I will. I'll contact you about that.
okay, get me through Brad. It's believe me, it's worth it. I've seen it now 3 times, and actually, as I said, worked on the detector, and it's probably the most expensive piece of space hardware ever built by humankind. And for that reason alone, you should see it.
Absolutely. Yeah, I would absolutely love to see it.